All right, good afternoon, everyone. Good afternoon to the panel, Dr. King, Dr. Puran Singh, the moderator, Ms. Gosain, colleagues and guests. I would also like to introduce my co-authors spearheading this project. We have Dr. Sangster, Professor Prasad, Dr. Maraj, Dr. Bisnath, Dr. Komabach, Mr. Bikram Das, and Mr. Edwards. So today I'm presenting a collaborative paper titled Smart Irrigation Estimator. And this is really to assist farmers in setting up a proper infrastructure that will utilize some of the natural resources. So this paper is a small part of an ongoing project that is in line with the national trust by the government towards food production. So this phase involves creating a smart irrigation estimator to determine water requirements as well as planting area for the plots. Now, over the last decade or so, our food import bill in Trinidad and Tobago has been increasing. Now, this is partly due to our population slightly increasing over the years, but more due to our lack of support and commitment to the agricultural sector. Now, Carney Lands, formerly Carney 1975 Limited, which was used for sugarcane production, was thought to be ideal for growing crops by the same farmers. However, the distributed lands were not developed for the farmers, hence no infrastructure, meaning no roads, no power, and no water supplies. Now, to assist the farmers in their decision-making process, we decided to create a user-friendly phone app that a farmer could understand and use. Now, this is just the initial stages of the app. The app is not finished, but we built a foundation on Microsoft Excel. So today, only the foundation of the app is being presented as a proof of concept. So this was done again using Microsoft Excel, and the objective was to provide a simple tool to estimate the water requirements and water storage based on the number of crops that the farmer wants to plant, the type of crops, our rainfall patterns, and the land available. So our methodology followed, we looked at our literature survey, we looked at some of the existing estimators, and we found CRIWA and CropWatt. Now, these are not user-friendly to the layman because it needs an operator to, who is proficient in software. Data was gathered on crops, meaning, the crop water requirements, our crop cycles, and our crop area per plant. From that, now we developed a proof of concept using the Excel to develop the estimator. And then we tested some different scenarios to ensure functionality and to determine, how useful this estimator could be. So using our design process, we came up with a functional chart or a fast chart and determined our inputs and our outputs from the estimator. So we wanted to input our planting area available and the start month to start growing the crops, a well size for our water storage, the types and number of plants, and a tool shed area to store our tools and produce on the same plot. Our outputs, we wanted to manage our water usage, our storage, know our storage for water deficit, our land use, and our available land. So our data gathering, we use the basic or the smallest plot available, which was the 2-acre plots given to the farmers. Based on prior knowledge, we estimated a tool shed size and a produce size. And from that, now we could have determined the planting area. Some assumptions made: the volume of water. Initially, we assumed that our water storage was 100% capacity. And we use for our crop cycle, the maximum crop cycle period to ensure that we could cater for the maximum water requirement. So this table just shows some of our data collected for our various crops. So for example, we have pepper, which requires a 9-meter square area and requires 900 millimeters of water, which converts to a volume of 0.9 meter cube. And we use the upper end again for the maximum crop cycle, which is 210 days. We also looked at our rainfall data, and we took it from two sources and used the average. Now, we also know that, rainfall is variable, highly variable in Trinidad and Tobago, but it's really just to use as a feed, as a demonstration for the estimator. For our results, and this is how the actual estimator works. We took a snapshot here where you could enter the acreage, and we use here 15% of that total acreage as a well storage. And here we entered the area for the tool shed and the produce. We estimated our well size to be 2 meters deep. And from that, we calculated the volume. Now, the crop information here is where you'll be entering now the type of crop, the number of plants, and which month you want to start in the year. So for crop 1 here, for example, you'll see hot peppers, and the number of plants we used here was 500, and we wanted to start in January. So the estimator now, we got an area of 4,500 meters squared. The crop cycle runs for 7 months, and the monthly water requirement for this 500 plants is 77 meter cube. Now I will just switch between slides back and forth just to show the output from the estimator. And you will see now for crop 1, we had the hot pepper, and that occupies a land area of 4,500 meters squared with a water use of 77 meter cube. And also now that crop cycle runs from January to July. So if we come to the end of the table here now, it will subtract this area from the total planting area and give you the available land remaining and the water balance. So remember now we started with 100% capacity. And for that January month, the rainfall capture we have estimated here as 207 meter cube. Now, this is just a percentage based on some prior information, and we use around 40% capture. And that worked out to be 207 for January. And now that will add to the storage and minus the water usage for the hot peppers, which takes 77 meter cube of water per month. Now going back to the crop information, now the second crop number 2, we selected tomatoes, and we selected 1,000 plants. We wanted to start this in March, and that the effective planting area for the 1,000 tomato plants will be 360 meters squared. It has a crop cycle of 4.5 months, and the monthly water requirements is 213 meter cube. So now we come to column 2, crop 2, and you will see we start in March, and again the cycle is 4.5 months, so we go into July. The available land remaining, you will see that was subtracted from the previous land available. We also added here now the rainfall capture, and we will have now the storage balance, our water storage balance now being decreasing and increasing with the rainfall, as the case may be. Now you'll see I highlighted a green area here, and it shows a negative land area. Now, crop number 5 and crop number 7 overlaps into the second year. So it goes into the January and February months, and that effective planting area was still being used. Now we also started back the second year now, January and February, and we use here the same 4,500 and the 77 meter cube of water. Now, we cannot have a, we cannot have an negative land areas. All it means is that we have put in too much plants that we wanted to plant. So what we need to know is vary the estimator now to give us a positive value, and this can also occur for the water storage. So you can vary your crop rotations, you can mix and match high water plants with low water plants. So what we did to correct this, I'm just having a slight issue here with a pop-up. All right, so we varied now, we reduced the crop number one, the hot pepper. So from 500 plants, we reduced it to 400 plants. So the effective planting area reduced, and also the monthly water requirement. You'll see it changed in the estimator here in crop one. So it moves from 4,500 to 3,600 meters squared. And the available land now decreased from increased actually, from minus 2,199 meters squared to minus 1,299. So it still shows a negative available land. So we need to adjust the estimator again. And we decided now to reduce crop number 5, which was hot peppers again. So we changed it from 500 plants to 300 plants. And the effective planting area for that was 2,700 meters squared with an associated monthly water requirement of 46 meter cube. And now the estimator now, we'll see in January, February now, it went from negative to positive. So again, the estimator is really to help the farmer now find some sort of optimum planting estimate and rotation of his crops and which crops he can mix and match to suit his available water storage to get an optimum, let's say, an optimum result throughout the year. So in conclusion, the estimator can save time and money by simulating the various number of planting scenarios. And this will be based on, the land area again, the type and number of plants, and the volume of water that is collected and stored. Now, if for some reason there's a deficit, the farmer will have to find an external source. It will assist in maximizing the area usage and production costs by mixing high water crops with low water crops. And the estimator has the potential to be improved by including other factors. So we want to take it further and add things like giving an estimate on security, nutrient control distribution based on plant needs and growth stages, and also smart pest control systems. The recommendations taken, we would like to modify again the estimator to include and calculate bed sizes and drain sizes, with the drains leading to some catchment area. To power the irrigation system, we would like to use solar power, and this can be housed on the rooftops of the tool shed and the produce storage area. The water storage can also be contained under the tool shed and the produce storage areas, but then the capital cost will go up. The area can also be used for securing the pumps and filtration systems to prevent theft. And a lot of farmers face that now. The estimated volume of water deficit can also be used to determine the depth of storage and can be oversized to incorporate, if we have droughts, lack of rainfall, to cater for that. Right? These are some of the references that we use for this paper. The balance of them will be shown in the paper. I would like to acknowledge Mr. Sivanarayan Prasad for providing information for us based on this study. We'd like to thank BPTT for awarding us a grant to continue the research, and UTT for endorsing this research. I'd like to thank everyone for listening, and I will now take your questions.
Thank you so much, Aneil, for that. Another very interesting and relevant presentation. I think we're getting some really good ones in this session. Some questions here from Johnny Chu. Johnny asks, I'm familiar with CropWatt and the Excel sheet omits some key information in terms of expected rainfall and the type of soil. Are these necessary, and are there any plans to add it?
Yes, we would like to increase the library base for the app, but for now, we just wanted to have functionality and to see the usefulness. But to answer the question, yes, these will be taken into account when we actually produce the final app.
Great, thanks, Neil. Johnny's next question, I also had the same question. I just wondered what type of irrigation you assumed in your model. Was it spray irrigation or drip irrigation? And is there any sort of...
So currently we have other researchers working on different types, but the one that we are looking at is drip irrigation. Dr. Sangster, our co-author, she did some work into that and is currently doing some tests with drip irrigation for various plants.
Okay, great, thank you. Did you use any GIS information in the implementation of this model?
Not for this first model, no.
Okay, so this is just based on an assumed, is it an actual lot or is it an assumed lot?
Well, based on what was given out by the government and keeping in line with their trust, we used the actual 2-acre plot. So what we're trying to do here now is really just to help the farmer to optimize the plot. Because a lot of farmers right now will just randomly select what they want to plant, how much, and we want to just give them now the estimates for the water consumption so that they will have an idea of how to cater for it throughout the year during the crop rotation for their farm.
Yeah, thank you. Peter Punchong asks, can you explain how you're integrating theft prevention?
Right, so this is one of the preliminary studies, and what we are looking at is probably remote monitoring, and maybe we want to set up some sort of either recordings or live feed, so that a farmer could either look at his planting areas, or even have something to alert him that something is happening while he's not there. So we might include some sensors, and all this, we want to power it using the solar power and have some sort of storage based on the plot of land.
Great, thanks, Aneil. And my final question is that the title of this presentation is a Smart Irrigation Estimator.
Yes. So yes, we will need to maybe change or try to include all the other aspects that we want to include in the app to try and encapsulate everything that we are trying to do.
Great, thank you very much, Aneil. Really nice presentation. Exciting to see a bit of technology being applied to our much needed agricultural, or much needed technology applied to